Okay, so let's say you have a certain optimization problem. So first of all, what is an optimization problem? You have a certain function and you'd want to minimize it. You'd want to find x that minimizes this function. Well, if you have this problem like this in front of you, this is called an unconstrained optimization problem, meaning that it has no constraints. On the other hand, if you're constrained by some constraints, then let's say I have M inequality constraints and P equality constraints. So those are your inequality constraints. This guy right here is called the cost, or also the objective function. What else do we have? Well, x is your optimization variable, right? Because this is what you would like to find at the end of the day. And yeah, that's all the terminology you should keep in mind. So this problem right here is an optimization problem put in its standard form. So any optimization problem you have, you can convert it or reformulate it to this problem in front of us. If you had a max of a certain function, then one way is you could insert a negative. So it's as if you're minimizing the negative of the function you're maximizing, right? So minimizing f is the equivalent of maximizing minus f. Now, what is the objective here? What are we trying to do? So the objective is to solve this problem, right? However, we have some cases. We face some cases while dealing with such problems. So if we denote P star as the inf or the infimum of my function, right? If I say this, then P star minimizes F0 without taking into consideration my constraints. However, I have some constraints, so such that it satisfies my constraints. So what cases could we face right here? We could be in a case where, P star is plus infinity, P star is minus infinity. Oh, so what does that mean? If P star is plus infinity, means that the problem is infeasible. It means that no x, no value x, could satisfy my constraints. So let me give you an example. Let's say one of your inequality constraints is, all x's that are, in this region. So let's say this line is minus x plus 1, right? And another inequality constraint is telling you, so you have to have all x's to the top of another line, which is, let's say, minus x plus 2. It is so clear that there is no x that could satisfy both constraints. So it's as if you have two people, one of which is telling you, well, can you lend me $10? And the other one is telling you, oh, well, can you lend me $20? So to satisfy both, you should have money, right? Well, what if you have $5? Okay, you can't satisfy any, right? So in that case, you say that the solution to my problem is infeasible. My problem is said to be infeasible. Now, on the other hand, if P star is minus infinity, means that the problem is unbounded below. So when f takes on the value minus infinity, no matter any x you pick as a minimizer, there's always going to be another x that could do better. That's what it means. It could do better in a sense that it satisfies your constraints and, it achieves a lower cost, because here better means lower. So the lower f is, the better. Okay, so now let's discuss two types of points. So one is optimal points, right? The other ones are termed locally optimal points. Now we'll talk about those in more details. But before, let's go ahead and define what a feasible point is. Right here, when we discussed P star, we say that the problem is infeasible or the problem is unbounded. Right here, we say that x is feasible, so it is a feasible point when x is in the domain of f0, right? That's one. And two, when x satisfies my constraints. What does that mean? Let's stop here and look at this definition. X in the domain of f means that there is an output, there is a cost for my given x, right? That's one. And two, X satisfies my constraints, means that it is a candidate. It is one candidate. It might solve my problem, depends on the cost. Now, how do we say that, X is the solution or the best candidate? It is when it is optimal, right? So when do I say that my X is optimal? It is when the cost at X is P star. And what is P star? The infimum of this set. And that's it. And usually people denote all optimal points as X opt because, the optimal point is not necessarily unique, right? So this defines optimal points, what an optimal point is. And now there is also something called suboptimal points or locally optimal points. So when do we say that X is locally optimal? It is when, if there exists a radius R such that X is optimal for the following problem. Minimize over Z, same cost function, f0 of Z, but this time subject to all your inequality constraints and your equality constraints. So right now nothing has been done differently. So this is the problem in standard form. But there's one more thing. It's when also there's an additional constraint saying Z minus X in L2 norm is less than R. Okay? So the problem with this additional constraint. If X is optimal for this, then it is locally optimal for this. So for the problem that we initially had, right? Of course, your task here is to find such an R. Now let's give some examples right here. So examples would be the following. So right now we're going to set n equal to 1. We didn't state that previously. I'm sorry about that. So right here, X is in Rn. So we're working in an Rn space. Okay. So with n equal to 1 means that X is in R. And we're going to set m equal to p equal to 0, which means that we have no constraints, which also means that we're working with unconstrained optimization problem. If I'm working with the following cost, 1 over x, the domain of f naught r plus plus. So the first plus means that non-negative numbers, non-negative real numbers. The second plus means we're excluding 0. So all strictly positive real numbers. And what is p star for this problem? So what problem? It's minimizing f0. So when you're trying to minimize f0, the minimum f would be 0 because on R++ it looks like this. And if you're minimizing, what is a point that could achieve this f0? There's none. And therefore we say x opt, is phi. So there's no optimal points for this problem. Because no matter what x you're going to pick, there's always going to be another x that comes right after it that does better. Another example could be minus log x or log 1 over x. If we define the DOM of f0 to be r++, the question is, what is p star in this case? So what is the minimum value minus log x could take? If we take a look at minus log x, so log x does something like this, right? So minus log x would do that. The infimum here is clearly minus infinity. And is there an x that achieves this? No. So x opt is phi. Again, because no matter what x you're going to pick, there's always going to be an x that minimizes f0 more or does better. Another example could be the log entropy or the negative entropy function x ln x. If we're restricted to r++, again, what is p star in this case? So x ln x is going to look something like this. It peaks somewhere here. Depends on the basis of, the log. In this case, it's the ln. So the negative entropy would do this. And this is clearly the optimal point that achieves p star. What is p star here? And what is x opt here? If you want to derive it, you can do traditional calculus, f prime, which is ln x minus x times 1 over x, which is ln x minus 1, set it to 0. So ln x would be minus 1, and therefore your x would be 1 over e. That is indeed x opt. To find p star, all we have to do is, in this case, it's f0 of x opt. We're going to have a 1 over e ln 1 over e, which is minus 1 over e. Okay, one last example would be, take f0 of x as x cubed minus 3x. What is p star in this case? Let's say my dom over here is all r. So x cubed minus 3x, it's clear that the p star here would be minus infinity. However, an optimal solution here is not achieved because, as discussed in minus log x, there's always going to be an x that does better, so x opt is empty. Likewise here, my x opt would be empty. However, there is a locally optimal solution. Let's take a look at the derivative first of all, f0 prime of x. So it's 3x squared minus 3, set it to 0. We've got an x squared equal to 1, and hence we've got x is equal to plus or minus 1. And if I open MATLAB to see how this function looks like, I define an x-axis going from minus 5 till 5, right? And I'm going to define my function. Now let's visualize how the function looks like. Okay, let's take a look here. Let's see what's going on. So if I take a look at those 2 points, minus 1 and 1, indeed they're not the optimal points because clearly there's a point right here, which is minus 5, that is minimizing my function more and more. Means that minus 5 is doing better than minus 1 or plus 1. So if I grab my data cursor and I place it here at 1, so we have a minus 2, right? If I go to the right, if I'm wiggling around 1, you know, I'm better than my neighbors, right? So this point, x equal to 1, is doing better than those to the, sufficiently those to the left, and sufficiently those to the right, right? So if I take a look at, you know, x equal to 1, it's doing better than some points. At least it's doing better than all the points to the right, right? And to some of the points to the left, until we reach somewhere, let's say here, because f at 1 would give me minus 2. So all points lower than minus 2 are doing better than x equal to 1, right? So what does that mean? It means that x equal to 1 is a local optimum point, because x turns out to be optimal for this problem. So there is an R in which my problem, so if I draw a circle here, I ask myself a question: is x equal to 1 optimal for this region only, for minimizing the problem in this region only? Yes. What is this R? Well, I could pick an R that is, you know, 0.1, right? I could pick an R which is 1, right? However, if you come and pick a point here, and I solve the same problem, let's draw a really small radius. Does it work? Well, no, because the point just to the left of it is going to do better. So if you're on a monotone function and you pick one, you know, point, then there's always going to be a point just next to it that's doing better. However, this is not the case when you're at the local optimum, which is x equal to 1. Because if you draw a circle right here, it's at least doing better than the one on the left and the one on the right. So this is the one on the right of x equal to 1, and this is the one on the left. So minus 2 is clearly less than minus 1.971, and it is also clearly less than minus 1.969, and therefore a radius of 0.1 would do, and that's it. Is there a larger radius? I don't care, but yes, there is. R equal 0.2, 0.5. It stops once you reach, you know, a point that is better, and that is minus 2.1, or yeah, minus 2.1. Minus 2.1 does better than x equal to 1. Therefore, a radius covering a region that includes this point, this radius is not going to work, okay? And that's how you could visualize a locally optimum point. Okay, so now let's go through some new terminology, which is explicit and implicit constraints, in case you face them. So explicit constraints are, nothing other than those constraints you see in front of you. So fi of x less than 0 for all I, and hi of x equal to 0 for all I going from 1 to p. So all those constraints are there in front of you, and hence they are explicit constraints. Means that they're just written in front of you, right? On the other hand, implicit constraints are those that are not in front of you. So what I mean is this. Let us first define a domain, call it D, which is the intersection of all domain of definitions of my constraints. So in other words, it is the intersection of, oh, and by the way, including the cost function, okay? So I equal to 0 is going to be the domain of f0 of x. So also intersected with the intersection of the domain of my h functions. So this set is called the domain of the optimization problem. Because if there's a point that should solve my problem, if the point is the best point, it satisfies my constraints and achieves the best cost, then it should belong to the domain of the problem. Now, in all those examples we gave, m was equal to p was equal to 0, and therefore the problem had no explicit constraints. I didn't come and, force a constraint on you, telling you, but you should solve, let's say, should minimize 1 over x, where x plus 1 is less than 5, let's say, for example, right? So you're in that case, restricted by this line, right? So you should be working only to the left of this line, right? So everything here. I didn't come and tell you that. Well, in that case, so when both m and p are 0, then my problem is said to be unconstrained, right? Simple as that. However, don't be fooled by, or don't be deceived by such a thing. Sometimes you could reformulate your problem by forcing those constraints out. Now, what do I mean by that? So let's say you're given the following, minimization problem or optimization problem. In this course, when I say optimization problem or minimization problem, it's going to be the same, unless I explicitly come and, write maximize. So minimize f0 of x, which is as follows: log b minus ax. I told you, as a mathematician or as an engineer or as a statistician or whoever you are, minimize this problem. And by the way, of course, since I didn't come and continue such subject to or such that, blah, 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 I have my m equal to p equal to 0, and therefore this problem is unconstrained. However, you do have some constraints, even though they're not in front of you. So if you want a feasible, point, you don't want any point that, that doesn't fall in the domain of f, and no one cares about this point, you have to be inside the domain of f. Meaning that in this specific problem, ax is going to be less than b, if you're going to pick an x, which means that x is less than b over a. So what did I just do right now? I forced a constraint on you, which is x less than b over a, right? So this problem is going to be the equivalent of the following problem: minimize f0 of x, which is log b minus ax, subject to my implicit constraints, which are x less than b over a, right? Or which is, in this case, we only have one constraint, right? So we went from an unconstrained problem to a constrained one. Now, one might ask, are those two equivalent? Let's be clear here. If I give you the above problem, the solution is clearly what? It's minus infinity. And therefore, going back here, the problem is unbounded, right? However, if you want a feasible optimal point or a locally optimal point, I don't know what you want, but at least let's say you want one of those three, which is most probably what you want, then you have to, at least work in the domain of f. You don't want to work on those, x's. So let me draw log x for you right here and show you what I mean. So let's say this is the log x function, and you're trying to find an x that, minimizes this function. So, if we go back here, then p star is minus infinity as it is, and therefore, the problem is unbounded. So there is no x that minimizes this function, because if you pick x equal to be 0, it's not in the DOM of f, right? Now, any x that is closer to 0 is going to minimize your function more and more. So the lower x is, the better. But you can't hit 0 because, it's not in the domain of f. So you can't come and tell me, hey, the solution for min log x is x equal to 0. No. And you can't come and tell me it's epsilon where epsilon goes to 0. No. So, people try to reformulate the problem in different ways that satisfies themselves. Well, to reformulate this problem, you're going to have to write it in an equivalent way as such. Perfect. So now, and at last, we've made it to this subsection of this course titled Convex Optimization Problem. So what is a convex optimization problem? So a convex optimization problem is indeed an optimization problem, and therefore I can write it as follows: minimize f0 of x, the same problem written in standard form. So I'm just copying this guy right here. But to say that this problem is a convex problem, right? And please don't mix up between convex sets, convex functions, and convex problem, okay? So convex sets, we talked about them. They're completely defined, right? Right here, we spent a lot of time talking about convex sets in order to spend a lot of time talking about convex functions, in order to come finally here and say what a convex optimization problem is. So a convex optimization problem is an optimization problem where your f's, or in other words, the cost and inequality constraints, are convex. That's one. And two, your equality constraints, they should be affine functions. AI transpose times x equal to bi. So this is a specific problem of an optimization problem, right? Because we're restricted to convex f's and affine h's. Yeah, that's what a convex optimization problem is, as simple as that. You could also encounter something called a quasi-convex optimization problem. So right here I might come and say quasi. It is the same thing, but only what differs is your f0. Only your f0 should be quasi-convex. Your fi's should remain convex. So you might encounter this problem written in a different form, but it's the same really. So minimize f0 of x, same thing, where it is convex, subject to your fi's less than 0. Those inner products could be translated to a simple matrix vector multiplication as such, where A looks like this. So A1 transpose, A2 transpose, down till AP transpose, right? And your B would be B1 down till BP. There's a nice property about convex optimization problems. So the feasible set of convex, I'm going to refer to it as CVX in short, of CVX optimization, OPT as optimization problem, is convex. And what is a feasible set? We talked about feasible set right here. So X is feasible if 1, 2, right? So all those X's that are feasible, collect them in a set and come here. If you're in a convex optimization problem, then the feasible set is convex. That's a strong property. So an example on this might be, let's minimize f0 of x, where it is a convex function. Let's pick a convex function. So let's say f0 of x is x squared. It's convex. Let's say my f1 of x is also a convex function, minus log x, right? And my h1 should be affine, right? So it should be something like ax plus b. x plus b, this, set it to 0, this should be negative, and this is the guy we're minimizing. So this is a convex optimization problem. Another problem that is not convex but could be, seen as an equivalent convex optimization problem is the following. So in case you're minimizing x1 square plus x2 square, now this is convex, subject to, why is it convex? You could check by, because it's differentiable in x1 and x2, then you could check using the first order condition or even the second order condition, right? So x1 square plus x2 square is nothing other than x transpose x. The Hessian is the identity. Do the derivative of this guy twice with respect to x1, you will get 2. Do it with respect to x1, then with respect to x2, you will get 0. Likewise here, and with respect to x2, you'll get 2. So it's 2i indeed. So this is the Hessian of f0, which is always positive definite. So f0 is convex, subject to f1, which is x1 over 1 plus x2 square, right? Now, is this guy convex? Let's check. Let's take a look at it in 3D. So x values, or my x1 values, are going to go from -2 till 2. My x2 values as well, and let's say my mesh grid those x1 and x2. Now let's plot my y, which is x1 square over 1 plus x2 square, right? Now let's surf. There you have the function. Does this look convex to you? No, it doesn't. It's clearly not convex. Take those 2 points right here. We pick this and this, right? The line is going to be below the curve. Whereas if you take, so it means it's not convex at least. Now take those 2 points here, it's on top. The line is on top. So it's switching, convex, concave. So there's no way to insert a negative and say, hey, I can convexify it because it's concave. No. Doesn't work. You can also prove it using the Hessian, that it is not convex, right? So this guy is not convex. And let's add one more equality constraint, which is not affine. So we'll take an affine function, square. And this problem is no way convex. However, there is another equivalent problem to this one that is convex. Equivalent, but it is not identical. Means you're not solving the same problem. This one we're going to leave it as it is because it's convex, but now we're going to change something. So here this is the inequality and this is the equality, right? So the inequality, we're going to come and say, hey, the denominator is always positive, right? There is no need to say x1 over 1 plus x2 square negative. I'll just say that x1 is negative because 1 plus x2 square is always positive. So to guarantee that this guy is negative, it suffices that x1 is negative. So that's 1, and this is convex because clearly x1 is convex, and more than that, it's affine. And the constraint, which is x1 plus x2 square equal to 0. So it's equal to 0. What does that mean? It means that x1 is equal to minus x2, right? So I can come and say this. x1 plus x2 is 0. So if this guy is 0, then I'm sure that the square is 0. So those two problems are equivalent, but not the same. They're not identical. What have we done with this conversion? This is not convex, but this is convex. And we're going to put a smiley face here because the name of the course is convex optimization. Yeah, so why do we want to do that? Why do we want to convert a non-convex problem to a one that is convex? Well, one main reason is because any local optimal point of a convex problem is optimal. And by optimal, we mean globally optimal. It solves our problem. So if we go back here, any x that is local optimal of a convex optimization problem is globally optimal, or is the optimal solution to our problem, right? So this is one really important feature or property for convex optimization problems. Now, similar to, the first order condition for convex functions, we have a criterion to say that a certain point is the optimal solution to the following convex optimization problems. So if this guy is differentiable, and we talked about differentiable in the previous lecture, we said that for a function to be convex, and if it is differentiable, then it must satisfy the first order condition, right? Namely, this guy right here, that utilizes the gradient of f. Okay, so likewise, when do we say that x opt, the optimal solution to our problem, is indeed optimal? Using the gradient of f0. We're going to use that because it is differentiable. Well, let's take a look at a certain function. Without, complicating stuff, let me just draw this function right here. Yeah. If this is an unconstrained problem, this is a local optimum because it minimizes f in the neighborhood of its surroundings. The global optimal is here for the unconstrained problem, of course. So this is my x opt. Using the gradient, what criterion could I impose on x opt to say that it is the optimal solution? Well, it turns out that if you draw the tangent at x opt, so let's say this is the tangent, so this function, or this line, this tangent, will be written as such: f prime x opt, times x opt. Okay, so if we take a look at all other points, what is so special about this blue line? It's clear that, if I grab any other tangent, so let's pick this point right here, and draw a tangent through it with the same slope as x opt, as that at x opt, right? Which is 0. The slope is 0, right? Let's grab this local optimum as well. Insert a tangent right here. So what is so special about, the blue line? It's always lower than other lines with the same tangent passing through the other points, right? So it's always lower. It's always like a lower bound. So in other words, we can come and say f prime x opt times x opt is always less than f prime x opt, but this time times any other point, and more formally, any other feasible point, because we want those points that, satisfy also the constraints and belong to the domain of f. I don't want to pick any other point that is not in the domain of f. So in higher dimensions, the derivative is replaced with a gradient f at x opt. Now this times transpose x opt, because we're working with vectors right now, is less than the gradient again at x opt transpose, this time y, where y is any other feasible point. Written differently, you can come and say the gradient of f at x opt transpose, if I can factor y minus x, and say it's positive. So this is my optimality criterion for differentiable costs. Indeed, for all y that are feasible. So as we said, if we want to, visualize this more clearly, if in higher dimensions and for all feasible points, so if we collect all feasible points in one set, and this set has to be, as we said here, feasible set of convex problem is convex, right? Let's do something like this. This is convex, right? So if I collect all feasible points right here, so all y's, if you will, feasible points, y's, let's denote this set as uppercase x. Then what is the role of, del f? And this, by the way, is f naught, my bad. So indeed, because we're talking about the cost, right? So differentiable costs. So all this is for f naught of x, namely the cost. So without, loss of generality, let's put it here on the boundary. So this is x opt. And what does the gradient of f at x opt represent with respect to this set? If it is non-zero, it will define a supporting hyperplane to the set x. So if I come here and I insert a line that is, let's say, tangent at it, the gradient, it is the normal, right? So this is minus del f naught at x opt. So this blue line is supporting hyperplane. Of course, we don't say supporting hyperplane and we stop. It's not a supporting hyperplane and done. Otherwise, any hyperplane would be a supporting hyperplane. It is a supporting hyperplane with respect to or on or off x. Informally, it means that, it supports it, it holds it from falling, if you will. Don't go ahead and say it to people. It's not correct. But what it formally means is that it is a hyperplane, as you can see, that has two properties. So one, x is entirely contained in one of the two closed half spaces bounded by the hyperplane. So in other words, the hyperplane shouldn't pass through the set. The set should be either completely on the top or completely below the supporting hyperplane. So that's one. And two, most importantly, x has at least one boundary point on the hyperplane. So there should be something in common between x and the hyperplane. So this is like, you could see it as a generalization of a tangent towards sets. Now, this is something really cool. Yeah, so this is what x opt is with respect to the set x. It's actually the hyperplane defined by the gradient of f0 at x opt. So the gradient will serve as the normal vector of the hyperplane. So the normal vector is pointing downwards in our case. So this guy should serve as a supporting hyperplane to the set.